Hello everyone, I am Noble Wadighare from Ramdev Baba University, a first year BTech CSE student from section A6. In this video, I will explain the topic Understanding Quantum Gates Operation with Quantum IBM Lab. We will explore how quantum gates such as CNOT, Hadamard, Fredkin, and Pauli Gates function and how to use them in IBM's lab environment. So let's start the video. So, what actually is quantum computing? Quantum computing is a type of computing that uses the rules of quantum physics. In normal computers, we use bits that are either 0 or 1. But in quantum computers, we use qubits. Qubits can be either 0, 1, or both at the same time. This is called its superposition. Also, qubits can affect each other using something called entanglement, which makes quantum computers very powerful for solving complex types of problems. So as of now, we have discussed about quantum computing. Let's now discuss about quantum gate. So what actually is a quantum gate? A quantum gate is like a logical gate only, which is in classical computers, but it works on qubits. This gate changes the state of qubits. Since qubits can be in many states at once, quantum gates do more complex things than normal logic gates. We use this gate to build quantum circuits and to run programs on a quantum computer. So, as now we have discussed about quantum gates, let's discuss about its types. So, there are various types of quantum gates. One of its kind is Hadamard gate, or we can say H gate. It is a type of gate, and it is one of the most important gates. It puts a qubit into a superposition. If we start with 0 and apply H gate to it, we get a 50-50 chance of getting 0 or 1 when we measure it. It's like tossing a coin in a quantum, just like it. So now let's discuss about polygate. Polygate, which is XYZ, there are which are the three basic gates: the X gate, the Y gate, and the Z gate. X gate, it flips the qubit. If the qubit is 0, it becomes 1, and vice versa. It is just like a normal NOT gate which we use in normal classical computers. Now Y gate. Y gate, it flips both the bit and the phase of the qubit. And the Z gate, it flips only the place, not the value. And here are the cascade command for the polygates. Now let's discuss about the CNOT gate, which is also called as CX gate. The CNOT gate is a two qubit gate. It has a control qubit and a target qubit. If the control qubit as just we can say 1, then the target qubit is flipped. But if the control qubit is 0, nothing happens. This gate is used to create entanglement between qubits. Here are the cascade commands for this thing where we can see qubit 0 is control and qubit 1 is target. Now, Toffoli gate, which is also called as the CCX gate because it is a three qubit gate, two controls and one target. It flips the target qubit only if both control qubits are 1. This gate is useful in quantum logic and circuits. In Qiskit, we write this code as like this, in which qubits 0 and 1 are controls and 2 is the target. So now let's discuss about the last quantum gate, which is Fredkin gate, which is also called as C-swap gate, as it swaps two qubits, but only if the control qubit is 1. This is useful in quantum circuits where we need to move data conditionally. It works with three qubits, one control and two target, which needs to be swapped. We can also try this in IBM lab using Qiskit, as we can see here the commands of the Fredkin gate. So from the start, we are discussing about IBM Quantum Lab and Qiskit. So what really actually an IBM Quantum Lab is? It is a website that we can where we can try quantum circuits for free. We can build circuits by dragging and dropping gates or by writing code in Qiskit. So now what is Qiskit? Qiskit is a basic Python library made for specific purpose for quantum computing. It allows us to create quantum programs, run simulations, and even use real quantum computers. So now, as we have done with the theory part, now let's get back onto the practical part. So I have used VS Code for this to run the Qiskit commands and to get the quantum computer, or we can say, and I have used Anaconda for this, which our lab ma'am said to do. So I have. So let's see. So here is the. Oh, wait. So here we can see is a Hadamard gate code in Qiskit, which is I will explain step by step once. So here we are doing from Qiskit import quantum circuit. So it is importing quantum circuit from the Qiskit, which I have installed in the Anaconda and in the Python. So then we are assigning QC value to the quantum circuit. Then we are executing the command qc.h0, which is the basic command for Hadamard gate in these quantum computers. And then we are then we are going to draw its circuit diagram. So here out how it looks, its output. So here is the Hadamard gate, which is which look like this. So now I just wanted to say that the Hadamard gate is used to put a qubit into a superposition, which I have already said. That means instead of being just 0 or 1, the qubit becomes both at the same time. It gives 50% chance of getting 0 or 1 when measured, which I have discussed already tossing a coin example. So that's all. And in Qiskit, we use qc.h0 to apply the Hadamard gate to qubit 0. That's all for the Hadamard kit. Now here for the Polygate, I have used the same. I have imported the quantum circuit again from the cascade, which I have given value it to the QC, which contains three values, which is X, Y, and Z. X contains 0, Y contains 1, and Z contains 2, which will draw it later then. And I will add upon this that the poly gates are basic single qubit gates in quantum computing. The X gate flips the qubit just like a NOT gate in basic classical computers. The Y gate also flips the qubit but changes its phase too. And the Z gate keeps the value the same but changes the phase. And these gates are very important in quantum algorithms and can be easily applied using qubit. That's all for the polygate. This is how it looks in the output. Now coming on to the CNOT gate, the same importing from the cascade of quantum circuit. The we have executed the command qc.cx 0, comma 1, which is a basic command for to run the CNOT gate. Now we will run the output and see how does it look like. So here is the CNOT gate for the this is how we display the CNOT gate. I will add upon this that the CNOT gate works on two qubits, which I have already said. The first is the control, and the second is the target. If the control qubit is 1, then the target qubit flips. But if the control is 0, target stays the same. In Qiskit, we use as we can see this command like this, where 0 is control and 1 is the target. Now for the Toffoli or CCX gate, the same thing, importing the quantum circuit function from the Qiskit, and we have used qc.ccx, which gives three values, which is 0, 1, and 2, in which the Toffoli gate or CCX gate. It has two control qubits and one target. The target qubits only flip if it only flips only if both controls are 1. We use this for more complex logic. In Qiskit, we write like this as I have written QCCX012. So this is how this output looks like. So this is a Toffoli gate. Now at the last, the Fredkin gate, which is also called a C-swap gate. So here I have here is the code for this, and also I will like to add upon it that the Fredkin gate is also known as C-swap gate. It swap two qubits, but only if the control qubit is one. So it checks the control first, and if it's one, it swaps the other two. In Qiskit, we use like this, as we can see qc dot cswap 012, and that's it for all the commands. So now let's take an example. Now, as we have discussed about all the gates and have run their commands in and their Qiskit commands. So now let's take one example. So here is this code which creates a bell state using Qiskit. We first import a quantum circuit and state vector. Then we create a two qubit circuit which Hadamard gate is applied to qubit to put it in superposition. Next, we can see here is a CNOT gate which entangles qubit 0 with qubit 1. Finally, at last, we use state vector dot from underscore instruction function to simulate the final quantum state and print it. The output shows the entangled state of 00 plus 11, which is a Bell state. So this is how we have done this example. Now, to sum up, we learned that the quantum gates are the building blocks of quantum circuits. We saw gates like Hadamard, Toffoli, Pauli, CNOT, and Fredkin. We also saw how to use Qiskit and IBM Quantum Lab to try these gates. Quantum computing is still new, but it has a great potential in areas like cryptography, optimization, and simulation. Thank you.